Okay, welcome back, all my beautiful pre-calculus students. Today we're going to be working on transformations, and I'm going to give you about 6 examples to show you the different rules that are going to apply with transformations. So I'm going to go through this kind of quick. Feel free to pause or rewind and play it again. But our directions today are going to be to graph each function and describe how its common or parent function is moved to create the new function that we're graphing. Okay, just a quick review of the common functions or the parent functions that we've learned so far. We have y equals x. We should know what that looks like. Y equals x squared, y equals x cubed, y equals the square root of x, y equals the cube root of x, and y equals the absolute value of x. And we will come into some more common functions like y equals 1 over x, y equals e to the x, y equals natural log of x, and so on a little bit later on in the school year. But right now we're sticking with these common functions, okay? So we're going to use transformations with these common functions. All right, that being said, let's go ahead and erase this and start our graph and follow our directions. We are to graph, and then we are to describe. Those are our 2 actions that we're going to have to box for our final answers, okay? Y equals x squared plus 4. First off, identify the common function that we're talking about. What common function do you see embedded inside this function, g of x? The common function would be just y equals x squared. And you can tell that something is being done to x squared to become g of x, obviously a plus 4 right here. So we have to know what y equals x squared looked like, and I hope you do. Just a quick little sketch without being too detailed with it. You should know that we have a parabola because it's a quadratic function, and our vertex is at 0, 0. We're also going through the points 1, 1, 2, 4, negative 1, 1, negative 2, 4, and so on. So let's go ahead and do some input-output combinations to get g of x graphed. Okay, so g of x. I'm looking at an xy axis. These are real number lines. So I'm just going to pick, let's say, 0. And I'm talking about an input-output combination. Y equals, g of x equals x squared plus 4. I could have said y equals if I wanted to, but I wanted to be particular about this being my common function and this being a different function, which is the common function with some kind of transformation or movement happening to it. So I'm going to pick 0. I'm going to put 0 into my g of x function. Square 0, I get 0, add 4, and I get 4. That means that I have an xy or input-output combination of 0, 4 that I need to graph. So I'm going to come over here. I'm going to go 1, 2, 3, 4. Here is the point 0, 4, and it's my y-intercept. I like always finding my y-intercept if I can. It gives me a place to start, initial condition. So I'm going to pick the point 1, and I'm going to plug 1 into the function. Substitute 1 in as your input. You take 1, you square it, you get 1. You add 4, you get 5. So my input-output combination that I need to graph as an xy coordinate point would be 1, 5. So I'm going to come up here to 1, 5. Every single time you plot a point, it follows with open parentheses, x, y, close parentheses. Not over on the side someplace. This does not suffice as labeling your points. So I'm going to try negative 1. Oops, sorry. Let's plug a negative 1 into the function. Negative 1 squared gives you 1 again. You add 4, you get 5. So negative 1, 5 is also a point on my g of x function. By now, I'm hoping that you get the gist of what this graph is going to look like. It's definitely looking like a y equals x squared graph, but it's going to have some kind of a movement to it. And I can see that y equals x squared is definitely being moved to become this graph. So I am going to graph this function. It's definitely a parabola, just like y equals x squared was. You could tell me that this is a quadratic function easily enough. And quadratic functions graph like parabolas in the shape of a parabola. So here we have this function, which is our g of x equals x squared plus 4. I'm going to erase the mapping that I have here that represents a function because each element in the domain is being paired with exactly one element in the range. So I'm going to erase this. and we are going to make a statement here about how the original common function, or the parent function if you will, is being manipulated to become this graph. So g of x, which is x squared plus 4, is y equals x squared shifted where? Up 4 units. And you could just say shifted up 4. As a matter of fact, it's probably a little nicer if I just keep that over in one line, so I will. Up 4 units. And we're good. We have graphed g of x equals x squared plus 4, and we have made a description of g of x in terms of its parent function, y equals x squared, or its common function. Notice I can't describe g of x in terms of its common function unless I give the common function. Okay, so I will box all of this because all of this is the answer to my directives, or to my problem. And we're going to move on with another example. So example 2 is going to say h of x is equal to the square root of x minus 2. And the first thing I'm going to ask once again is to identify the common function being involved. So the common function is y equals, and we had all 6 of them on the board a few minutes ago. Obviously the square root symbol is going to give it away. So y equals the square root of x. Again, you should know exactly what that looks like. We're going through the point 0, 0, 1, 1, 4, 2, 9, 3, and so on. So this is the general idea of what y equals x squared looks like. Not being too particular, but it gives the idea out there. So now we're going to graph. H of x is going to equal the square root of x, quantity, square root of x, and then minus 2. So here's my x-axis, my y-axis. And let's go ahead and do some input-output combinations. Let's draw a mapping here for h of x, which is equal to the square root of x minus 2. And let's pick some nice numbers, some friendly numbers for our domain, or our x's, or our inputs. Again, I like that 0. So square root of 0 is 0, and then minus 2 gives me negative 2. So 0 is paired with negative 2 with the h of x function. So I have to plot the point 0, negative 2. Again, this is my y-intercept. I like my y-intercept. I'm going to pick the number 1, and I'll put 1 into my function. I pick any number I feel like picking, and if I pick something and it doesn't turn out quite right, I could choose to go back and erase that and just pick something else. It's up to me. It's my discretion. Square root of 1 is 1. Take away 2 is negative 1. So 1, negative 1 is an xy coordinate point that needs to be plotted. Now, do you think I'd pick negative 1 to go into that radical symbol right there? And I hope you're saying no, because the domain of my common function here is anything greater than 0, or equal to 0. We did 0, obviously. Greater than or equal to 0. It's just that you can't have a negative radicand under an even root sign, just like we practiced when we did domain of analytical functions. So if I put a negative 1 in here, I'd get stuck. That would be the square root of negative 1, which is I, which is an imaginary number, and like I said earlier when we first started, the x-axis, the y-axis, those are real number lines, okay? We're not graphing complex numbers or imaginary numbers, so that cannot be in my domain. It's gone. So should I pick a 2? Square root of 2, I don't really like around 1.4. I'm not going to graph that one. I'm choosing not to. Square root of 3, I'm choosing not to. We're about 1.7. I don't want to do the square root of 1.7. So I'm going to try 4. And I'm going to put a 4 in to my h of x function. I know I was pointing up here, but h of x is this common function being manipulated, so I'm okay looking at that. Square root of 4 is 2. Take away 2 is 0, so 4 is being sent to 0. I'll come over here and plot the point 4, 0. And if I wanted to pick one more number, I think I would probably pick a 9. The square root of 9 is 3. Take away 2 is 1. So I might plot the point 9, 1. I might not. 9, 1. That would be over here quite a bit, right? And up a little bit. So 4, 5, 6, 7, 8, 9, 1. I guess I'll put it there and just write 9, 1. But my axis isn't allowing me to go there because I have stuff in the way. This function is going to start at 0, negative 2. It's going to climb up kind of fast, but then it's really going to taper off and it's not going to climb as fast. The further to the right you go, the slower and slower it climbs. It continues to climb. We're going to have a range here of positive infinity, from -2 to positive infinity, and my domain is going to continue to move to the right to positive infinity, but it tapers off a little bit and doesn't climb very fast. Okay, so this is going to be gone. And I'm going to clean this up just a little bit, just because I want it looking nicer. There we go. All right, so now I need to describe this function, this h of x equaling the square root of x minus 2, in terms of its common function, y equals the square root of x. So let's just write it down. Let's write h of x equals the square root of x minus 2 is y equals the square root of x, the common or the parent function, shifted where? And in this case, this function is being shifted down 2 units. You can see that the point 0, 0 became 0, -2, so we're dropping down 2 units. All the other points respectively drop down 2 units to become the new points that I have graphed. So we're going to say down 2 units. And I have my graph, I have my description, so I'm going to box this, everything. And I'm going to create a rule for you. Okay, so I'm going to come over here, I think, and I am going to write rules. And I'm going to put these as succinct as I can, but at the same time, I'm going to make sure there's no confusion going on here. So one of my first rules is going to say something like, g of x, or instead of g of x, I think I'm just going to say y equals, because it can be g of x, or h of x, or k of x, or q of x, or r of x, or whatever I want. So I'm just going to indicate that it is a y coordinate. Y equals my common function, which I'm going to, let me see, did I not do an f? Okay. F of x plus c. Y equals f of x plus c, where f of x is my common function, is f of x shifted up c units. And I want that to kind of look like this first example over here. So I have y equals my common function f of x plus 4. And that means that it is the common function, y equals x squared, shifted up 4 units. And the 4 is my c value over there in that statement. C is representing a constant. So when you see a plus c on the end of a common function, and it's just plus 2, plus 3, plus 4, plus 5, anything plus c, you just know that you're going to go up c units. Okay? And just like you could go up, you could also go down. So y equals f of x minus c is f of x shifted down c units. And these two rules right here are, let me see what good word describes up or down, mathematical word that could describe whether you shift up or you shift down. You shift what? Vertically. So these are vertical shifts. Now if you read this in a math book someplace, they're not going to give you 2 rules for a vertical shift. They're going to compose those and put those down as 1 rule. So I'm just going to trigger that just a little bit, and I will say something like y equals f of x plus c is f of x shifted vertically c units. I don't know why I always want to hyphenate that. Alright, f of x plus c is f of x shifted vertically c units. So if c is positive, we go up, and if c is negative, we go down. Up here, I'm just presuming that the c value is just a regular counting number or positive number, I guess is what I'm assuming. But so if you see a negative c, like this, we're definitely going down 2. But according to this rule, if I looked at this plus c like this, and I tried to compare it to this, I would say that my c value is negative 2. Okay, so obviously that would mean you're going down 2. Alrighty. One more thing I want to emphasize on this particular transformation of common functions is that when you do a vertical shift, the change that you see in the function is always occurring after the common function itself gets executed. I'll talk about that for just a minute, but you're going to hear me saying that over and over and over again. When I did my input-output combination for g of x over here, I squared first, and then I added 4 because of my orders of operations. If you square first, then you are executing the common function first, and then you're making the change happen second or later. When the change happens after the common function is executed, you are always affecting the y-coordinate. You are not affecting the x-coordinate. So if you think of y being x squared and me taking this x squared and replacing it with a y, when I take a y value and add 4, I'm changing the y value. So I'm either increasing or decreasing the y value, which would mean I'm going to go up or down. So a plus 4 on x squared is going to shift you up. That is a y change right here because this plus 4 is being executed after the common function is executed. Likewise over here, when I put my 9 in, the square root of 9 is 3, and then I subtract 2. So I've executed the common function first, and then I subtract 2. So this minus 2 is actually affecting the y-coordinate of all of my points of the common function, and not the x-coordinate. So we'll see how that's going to play out as we move on, because obviously we're going to mix it all up, and it's all going to be given to you at one time, and you're going to have to keep things straight. So we're going to cut this video right now on these vertical shifts, and you should now know how to work transformations of vertical shifts. All right, talent out.